Good morning. I wish to thank the scientific and organization committees of the first International Conference on Sustainable Energy and Advanced Materials for this opportunity of presenting our latest works and the global pandemic situation. Our today's presentation is about electrodeposition and characterization of nucleoxide on ETU glass substrate. The table of contents, four main titles, which are Introduction, Experimental Techniques, Results and Discussion, and finally Conclusion, will be discussed. First, we'll present the nucleoxide properties regarding his band gap, which is between 3.5 and 4 electrovolts. Furthermore, we selected nucleoxide for his absorption in the visible region, with a refractive index equal to 2.33. Finally, the nucleoxide have cubic structure like an NaCl molecule. After searching in the literature for the properties of nucleoxide, now we will cite several applications which are batteries domain. Thin film transistors take place commercially in today's technologies such as flat panel displays, smartphones, and computers. Photovoltaic cells employ the semiconductor materials to convert the light into electricity. The nucleoxide nanoparticles can be used for catalytic and gas sensor applications. Now we pass to the experimental techniques that we used. An electrochemical cell related with potentiostat and the thermostatic bath to control the temperature were used in the experimental procedures. Inside the electrochemical cell, we have three electrodes which are reference electrode type ECS, working electrode. In the study, as we mentioned in the title, we used an ETU substrate. And finally, a platinum wire was used as a counter electrode. That's for the electricity part of the cell. Putting all those chemicals, we will have a pH equal to 12. The temperature of the solution was fixed at 70 degrees. For results and discussion section, two main parts that will be presented. The first part is the electrochemical study, which included chronoamperometry and Mochotsky measurements. The chronoamperometry was used to deposit our thin films of nucleoxide on ETU glass substrate. The present curve shows a typical response of transient current of three-dimensional nucleation and growth process. The charge quantity increase with the increasement of the deposition potential. This increase is due to the rise in the deposition speed of our oxide as a function of the cathodic potential. Mochotsky measurements were used to identify the semiconductor type and the carrier density value. The negative slope of the curves indicate that all the nucleoxide thin films are a p-type semiconductor, with the carrier density varies irregularly between 0.75 to 1.38. Characterization. The second part presents characterization techniques that we used. Structural characterization by X-ray diffraction was presented to show the crystallographic parameters for the cubic structure of nucleoxide. The values of the diameters vary randomly between 50.91 and 64.91 nanometers with the applied electrical potential. The optical characterization by UV visible was studied. On the other hand, the optical transmission of nickel oxide deposit decreased from 55 to 25% the visible range, as the deposit potential increased from minus 1.30 to minus 1.45 volts respectively, with the shift of the absorption edge towards the blue curve. As a conclusion, Mochotsky measurements confirm that nickel oxide thin films are p-type semiconductors with a charge carrier density of around 10-18 centimeters. X-ray diffraction analysis show that the nickel oxide nanostructure have cubic phase. The study of the optical properties of the deposits indicate that the optical transmission decreases with the potential. Finally, the optical band gap of nickel oxide deposited different potentials are determined from the torque relation with a range between 3.88 and 3.97 electrovolts. Thank you for your attention.